Hi everyone. Today we're going to have a look at the mini mock questions from just before the half term. Going through the higher level questions now. Now I'm going to try and keep this as brief as I can, guys. The last video for the ordinary ones racked in at like half an hour. I'm going to try and truncate that a little bit and keep it a little bit briefer. Now with that in mind, my diagrams here are going to be a bit messy. My handwriting is going to be a bit messy. But remember, all of the key definitions and key kind of equations are all in that handout that I gave you with there's about 6 or 7 pages with with all the definition-y stuff kind of condensed. So if I'm referring to that, that's going to be a bit more exact. And that being said, I still aim to get the core of each question. But as I say, my diagrams are sometimes a little bit messy. Just bear with me because this is take 5 of trying to make this video. I've had a load of technical problems. It's been a while. All right, so warnings and excuses aside, let's just horse into it. So we've got the high-level questions. And make sure, again, before you watch this video, make sure you've had a try at these questions yourself, okay? It's been a couple of weeks since you've done them, you've forgotten them. Refresh yourself on the question itself. Otherwise, you're just listening to me talk at you for what may be 20 minutes, half an hour. So make sure you've had a go at the questions yourself before watching this video. Okay, question 1. The magnets in the Large Hadron Collider operate at a temperature of 1.92 Kelvin. Convert this value into Celsius. So I gave you this kind of handout of useful formulae. Now remember, on the day itself, you won't have this. You'll have the logbooks. So I'm going to use these kind of things less and less so that you get a bit more comfortable using the logbooks because that's what you'll have on the day, just to retrieve this information and equations yourself. But here's the first equation we're going to use. The Celsius temperature is equal to Kelvin minus 273.15. Now this one's nice and straightforward. Often they'll ask you to convert from Celsius, in which case people often fall in the trap. Let's say they give you a Celsius value, like body temperature was one, I think, on the order of the question one, and they just sub it in. But you can't just sub it in. You might have to do a little bit of rearranging then. So if they give you a Celsius value, you're going to have to bring that 273.15 across. I'll show you a little tip in a moment as to how to see if your answer makes sense. But in the meantime, they haven't tried to trip us up today. They've just given us the value in Kelvin. So to get the value in Celsius, it's our Kelvin value of 1.92 minus 273.15, which is still on there from when I tried it a moment ago. 1.92 minus 273.15 is equal to minus 271.23, and now to put on our units, degrees Celsius. Now the way to see if you've done it right or wrong is if you get a Kelvin value that is less than 0, something's gone wobbly, because remember, absolute 0 Kelvin is as cold as you can get. So you can have a negative Celsius value, but you can't have a negative Kelvin value. But that one is nice and straightforward. Just sub in the values, and that's your answer. The second one is not straightforward. The second one, this is from last year's paper. And first off, before I begin, I owe you an apology. When I made the test, I scanned through it and made sure all the values were there. What I didn't realize is that StudyClix had cut off, this was part of a bigger question, and they cut off one piece of information you needed, which was the heat capacity of water. They also cut off the density of fresh water being 1 kilogram per litre. That 1 litre is equal to 1 kilogram of mass. Sorry, 1 litre of water is equal to 1 kilogram mass of water. They also cut that out, but it wasn't really pertinent. This one was very relevant, and I apologise if this threw you because it is a necessary part of the answer. Now, not making excuses, because I'm not, because there is no excuse. That value is given later on in the experiment question, but I wouldn't expect you to be retrieving that and going back and forth. On the exam, that will be on the question. It's just, as I say, someone was sleeping at the helm, and then so was I. So apologies, but let's just have a look at it anyway. Okay, so the Bronze Age began about 5,000 years ago. Archaeologists used physics to help them understand the culture and technology, one thing they did was make this flucta fia. So when they dug a hole in the ground, filled it with water, and then threw some hot rocks inside, and the hot rocks would heat up the water, and they could then use it, we think, to cook food, maybe. Now, given the temperature that we're going to get as our final answer, it doesn't look like we do much cooking, but whatever, let's force into it. So they threw in the stones, heated the stones, threw them in, and it would cause the temperature of the water to increase. So before we get into the calculation part, what is meant by heat capacity versus specific heat capacity? So heat capacity, and remember, if I don't write this very neatly, it's all on that handout that I gave you. It's all in your textbook as well. But heat capacity is the energy required, so I'm going to be using abbreviations and stuff, to increase the temperature of a body or an object, just call it of a body, by 1 Kelvin. So heat capacity is energy required to increase the temperature of a body or an object by 1 Kelvin, obviously without causing a change in state. Whereas specific heat capacity is the one we're more often used to using. This question is a bit of an outlier in that sense. They usually use specific heat capacity. And specific heat capacity is the very similar, but not quite the same, energy required to raise the temperature of, and here's where it gets different, 1 kilogram of a substance, so steel, water, copper, whatever, by 1 Kelvin. So the difference there is heat capacity is referring to an object, specific heat capacity is referring to a material, and 1 kilogram of that material. Okay, calculate the highest temperature the water could have reached. All right, now this one's going to get a little bit messy. I'm going to show you, there's two ways we can do this. We could either look at it as, let's think of what's happening here. So they have their water trough, and they're chucking in some hot stones. So what's going to happen is the stones are going to heat the water. So you could look at it as the heat lost by the stones would have to be gained by the water. Or, the change in temperature caused by this heat exchange, heat gained by the water. But I prefer you to think of it more as adding all of the energy changes and equating them to zero. Now, this is a bad example of why we should do this. Question is a bad example of why this technique is better, because we're only dealing with two kind of changes. But what I prefer to think of, instead of one thing equals another, think of adding them. The first energy change, whatever that might happen to be, plus the second, plus sometimes there's a third or a fourth. But when you add them all up, they equal to zero. Now, I prefer it that way because the temperature changes will take care of the signs. You don't have to worry about things getting a bit messy. Whereas with this, you have to realize that one heat loss is going to be like initial minus final minus initial temperature, whereas heat gained is going to be initial minus final. It gets messy. I prefer you to think of it this way. Add up all the heat exchanges and sum them to zero. Now, if you're horsing through all the examples in the textbook and you prefer going via that method, or if it's more intuitive to you, you do that. Absolutely fine. I'm going to do it this way. It's a subtle and slight difference, but I think it just makes it make a little bit more sense. Okay, so I'm going to say that the heat lost by the stones, we're going to see that as a temperature change. So the temperature change of the stones plus, the heat used to change the temperature of the water would equal to zero. Now, in more complex questions, you might have things like changes of state or multiple materials, but this one's nice and handy. We've just got two quantities involved. The stones losing heat and the water gaining heat. And they should balance out as being zero. Okay, so let's think about this a little bit more and put in our values. Actually, we're a long way from putting the values out, I apologize. The temperature change of the water. Well, the temperature change of the stones, first off, is, well, let's write out the numbers. We have the number of stones is 50. The heat capacity of the stones is 8.5 by 10 to the 3 joules per Kelvin. So let's just convert that. First off, 85000. Oops, 00. So I'm just getting rid of the 1000 there. So it's 8,500 joules per Kelvin. We have water. Now here, let's look at the mass of the water. So they tell us that there's 750 litres of water. Now 1 litre of water has a mass of 1 kg. So 750 litres has a mass of 750 kgs. Now sometimes they can try and trip you up. You might have to use the density equation to figure out how much mass you have. But this time it's just 1 for 1. So they might do that in case if you're dealing with fresh water versus salt water. But this time we can take it that the mass of the water is 750 kgs. The initial temperature of the water, so I'm going to have to use a little IW for the initial of the water, was 4 degrees Celsius. The initial temperature of the stones when they came out of the fire was 280 degrees Celsius. And we don't know the final temperature of both. Now remember, the water and the stones will be at the same temperature at the end. So we can just say theta F, because it's going to be the same. And we don't know what that is. That's our target, that's what we're looking for. Okay, so let's go with the temperature change of the stones. So the temperature change of the stones is the number of stones we're dealing with multiplied by the heat capacity of the stones multiplied by the temperature change of the stones, which is the final temperature we're looking at minus the initial temperature of the stones. That's the temperature change. Sometimes we do that delta theta. So that, the number of stones times their heat capacity times the temperature change, plus we have to do with the water next. So that's the mass of water, heat capacity of water, temperature change of water. So that temperature change is the final minus and the initial temperature of the water. Just be careful, that's not the same as the initial temperature of the stones. When we add them, they're going to equal 0. Now, as I say, we're a long way from doing any substitution yet. Let's just we're looking for, this is our target, okay, the final temperature. We know everything else. We know the number of stones, we know the heat capacity, we know the initial temperature of the stones, we know the mass of water, the heat capacity of water, the initial temperature of the water. We just don't know the final temperature of both of these fellas. So that's what we're going to try and find out now. Okay, let's see, a bit of algebra first, I think. Well, do you know what it is? We'll multiply it. Imagine this as, let's just multiply these guys together first. So let's multiply the number of stones times the heat capacity times theta F. So the number of stones times heat capacity times the final temperature minus the number of stones times the heat capacity of the stones times the initial temperature. So I've just multiplied, kind of imagine this theta, delta theta as a set of brackets and then multiplying it out. Plus, over here, same thing. Mass of water, heat capacity of water times theta F, the final temperature, minus mass of water, heat capacity of water, and the initial temperature of the water is equal to 0. So I've just equated all my energy changes to 0, and now just because we're going to be isolating this theta F, I've multiplied out the brackets. There's a few different ways of doing this, by the way. If you've got a different route and you got to the right answer, all is good in the hood. So we're looking for theta F. So I'm going to bring everything with theta F to one side of the equation and bring everything else to the other. So we're going to keep the number of stones times the heat capacity of stones times theta F, and we're going to keep the mass of water, heat capacity of water times theta F. We're going to keep them on this side of the equal sign, and I'm going to bring everything else over. So let's bring this guy over first. Number of stones, heat capacity of stones, initial temperature of the stones. Just brought that guy across, and let's bring this guy across. That was a minus, becomes a plus. This is a minus, also becomes a plus. Plus mass of water, heat capacity of water, by the initial temperature of the water. Now, we're not quite there yet. Sorry about this guy. We're looking for theta F. So let's do a little bit more algebra on the left-hand side of the equation here. Just isolate theta F. So that's common to both of these expressions. So I'm going to factorize it here by taking out theta F from this whole mess. So that'll give us the number of stones, heat capacity of stones, plus mass of water, heat capacity of water. So I've just taken theta F out of this. Is equal to number of stones, heat capacity of the stones, theta IS plus by initial temperature of the stones, mass of water, CW, theta IW. Now we're looking for this on its own, so let's bring this whole mess across. So we have the final temperature that we're looking for is equal to this top bit, the number of stones times their heat capacity times their initial temperature, plus the mass of water, heat capacity of water, times the initial temperature of the water, all divided by, let's keep brackets around this, keep it a little bit easier, the number of stones times the heat capacity of stones, plus the mass of water times the heat capacity of water. Now, exhausting, but we have everything we need. Okay, we have our final target identified, and all these other variables are things we know. So it's just a matter of subbing in the numbers. Just a matter to see as it's easy. So we have 50 times 8.5 by 10 to the 3. I should have just written that as 8.5. Right. Times the initial temperature of the stones, which is 280. That's this bit here. Plus the mass of water, which is 750, times the heat capacity of water, which we said was 4180, times the initial temperature of the water, which is 4 degrees Celsius. Now you might notice I'm not converting into Kelvin here because the temperature change will take care of that. When you drop by 20 degrees Celsius, you drop by 20 Kelvin. So that'll all be good. Divided by 50 times the heat capacity of stones, 8.5 by, again, I've done it again, 8.5 10 to the 3. All good. Plus, these are all in brackets here to divide this whole thing. Mass of water, which is 750, times the heat capacity of water, which is 4180. Now, that's a mess. But when let's put it in and see what we get. So 50 times 8.5 times 10 to the power of 3. That's the first expression. Let's get some brackets around that. Plus 750 times 4180 times 4. Brackets around that. So the top part of this line is 1296500. We'll worry about units after. And I'm going to make life more complicated. I'm going to work at the bottom line. 50 times 8.5 times 10 to the power of 3. Plus 750 times 4180. So my bottom line here is 3560000. So 1296500 divided by our answer gives us a final answer. I've messed up a 0 here because let me just see. In my calculation there, I went wobbly by 0 because my answer here was 3.6 when I know it should be, just from doing this question so many times, 36.418. Now, it's unacceptable for me to ask you to just trust me. So I'll tell you what, let's force these numbers in again and see where I went wrong. 50 times 8.5 times 10 to the 3. Do it all in one line this time. No human error. Oops. Times 280. Plus brackets. 750 times 4180 times 4. That's the top line done. So get some brackets here and there. Divide by 50 times 8.5 times 10 to 3 plus 750 times 4180. Now that's more like, sorry if you think the audio went there, it was just me making sure that we got our right final answer. 36.94 degrees Celsius. So that's the final temperature. Now straight away, I've taught you to do a common sense check on an answer, okay? And this would kind of backfire in this, in my opinion, kind of stupid question because a final answer of 39.94 degrees, you can't cook much at 39.94. That's like a warm bath, all right? So this would backfire. If you got that answer and you thought, oh, it's a bit cold for cooking food, well, you're right. That's why we say that we only suspect they use it to cook food. They might use it to have a bath. Seems like a fairly laborious way of going to have a bath, but such is life. It might just be the values chosen for this calculation. But look, very long-winded way of saying final answer 39.94. That's a lot of like complex looking algebra. But you got to bear in mind that of all this, there was one thing that we did not know, and we knew everything else. So there are multiple roads that lead to Rome here. There are easier, there might be ways of doing that algebra that would work out easier for you. If you did that and it works out, happy out, Okay, none of this endeavour was happy, I think, for you guys. Let's crack on. All right, so that was the heat question. Now, how are we for time? We've been waffling on too much, probably, but no, nothing to be done. It's 4 time. Okay, the waves question. We've done this in class, but for the sake of completion, let's do it again. Hydroacoustics is the study of sound in water. The Doppler effect is measured in hydroacoustics. What is the Doppler effect? The Doppler effect is when you get a perceived change in frequency. So when you think that something has a different frequency because the source is moving towards or away from you due to the relative movement of the source. Now again, that's all in your handout, so if my definition there isn't precise enough, it should be pretty close to match that. So the Doppler effect is the perceived change in frequency caused by the movement of the sound source in relation to the observer. Describe how the Doppler effect can be demonstrated in the lab. Now we haven't done this. This is the one I was talking about where if you take like a buzzing bell, like an electric bell, and you swing it around and around in circles, as it approaches the observer, it'll have a different frequency from when it's moving away. So you'll hear it as a kind of raising and lowering pitch, like a siren. Okay, speaking of, we have to apply it. A moving underwater source emits a sound of frequency 800 kilohertz. Now normally, I convert that kilo to just hertz. Now this time it's not going to matter too much, but let's just do it anyway. Let's be consistent. So it's 800,000 hertz. So that's the frequency emitted, which we know by just F. And the frequency that's detected, we say that's an F prime, like what you think you hear, which is 806 kilohertz. Now, let's go to find which formula we might find useful here. So the Doppler effect should be here somewhere. Boom, Doppler effect. Okay, so the perceived frequency is equal to the emitted frequency times the speed of the sound divided by the speed of sound plus, or sorry, the speed of the wave, plus or minus the speed of the thing that's moving. Okay, so they give us the speed of sound in water is for 1,480 meters per second, noticeably quicker than in air, of course, because those particles are denser together. Now, let's think about which one we need here. So they heard a higher frequency. So if you can't remember whether to use the plus or the minus, let's just do a little bit of detective work here. We have an increase in frequency, right? The frequency sounds bigger than it is, which means that we're dividing by the smaller setup here, okay? Because remember, this is a fraction. If you divide by a bigger number, you get a smaller overall number. Like a half is bigger than a quarter, right? Because you're dividing by a smaller number, which means your overall total, because you're dividing it into less numbers, is bigger. I think I've lost you there. So with a fraction, when you're dividing by a bigger number, you get a smaller number. When you divide by a smaller number, you get a bigger number. Now we're looking for a bigger number. Our frequency's increased, which means we're using f prime is equal to fc over c minus u. Okay, now what are we looking for? I forgot all that. We're looking for u. We're looking for the speed of the actual object. So let's do a little bit of algebra as usual before we go any further. So let's bring c minus u across. So we have f prime times c minus u is equal to fc. I've just brought these brackets across. It was divided by here, it's multiplied by here. Let's bring the f prime across. So we have c minus u is equal to fc divided by f prime. And my final one, let's bring the c across. So I have, well, not my final one now because I've got minus u is equal to fc over f prime minus c. And because this is minus u, let's multiply both sides of this by minus 1. And that gives me u is equal to minus fc over f prime plus c. Or if you feel a bit more comfortable writing it as u is equal to c minus fc over f prime. Okay, here's me saying f prime without reminding us of what we're dealing with. So u is the velocity of the thing that's moving, c is the velocity of the wave in that medium, frequency of the sound produced, and f prime is the frequency we perceive. Now we know all those numbers, so let's put them in. So the sound is equal to the speed of sound in water, which is 1480. I'll leave out the units for now. Well, actually, no, let's not be lazy. Let's put them in meters per second. Minus the frequency that we perceive, sorry, the frequency that was produced, which is 800,000 hertz, divided by, multiplied by 1480, the speed of sound in water, all divided by the perceived frequency of 806,000 hertz. Now this is what I was saying earlier on. This time the kilo thing doesn't matter too much because the thousands are going to cancel each other out, but it's still good practice to do. So before we put this into our calculator, let's cancel off what we can. These guys are going to be gone, these 4 zeros, in fact the 5 zeros are gone. So we have, oops, no, yeah, Wally, that's a 6. Okay, so we have 800 over 806, 480. Okay, I didn't really need to do that, to be honest. That was fine, just lower horse into the calculator. So 1480 minus, and in brackets we have 800,000 times 1480. Some double brackets around this. Divided by 806,000. Syntax error because I added one too many brackets. So I got a final answer there of 11.01 meters per second, which isn't a mental answer. That's a fast moving object, but it's not crazy. Remember, if it was moving at like the speed of light, something's gone wrong. Okay, long-winded question. Is that the end of it? It's not. Okay, sound wave. Okay, do you know what? If the last one melted your brain, it's going to happen again. So this is a tricky one. Sound waves travel faster in water than in air. When a sound wave travels from water to air, it undergoes refraction. Draw a ray diagram to show the refraction of a sound wave as it travels from water into air. So the trap here is you're so used to talking about rays of light emerging from water, and when they emerge into a faster medium, they're going to bend away from the normal. You're used to thinking about like light moving from a dense material into a light one, into a rarer one, and light moves faster in this than it does in this. But sound is the opposite. Sound moves slower in air than it does in water. So that is incorrect. Here's your water, here's your air, and your ray diagram. Let's say we have sound wave emerging like that, and it actually bends towards the normal, which I should really draw in here. Good habit. So there's your incidence, there's your refracted, because it's moving into a slower medium and bends towards the normal. Just like if you think about light going into a glass block, it bends towards the normal. That's the classic example. You've got to be careful here. They're a little bit sneaky. So this is the correct answer. That long-winded kind of waffle fest. Okay. Second last question. Distinguish between a vector and a scalar. Okay, a vector has a magnitude and a direction. Whereas a scalar only has a magnitude, doesn't have a direction. Draw a labeled diagram of the arrangement of the apparatus in an experiment to find the resultant of two vectors. This is the one where we have 3 Newton meters all attached to. You can either have like a string with a knot tied in a string with 3 pieces coming off, or you can just hook the Newton meters together. So we've got 3 Newton meters. And for the sake of making this clear, I'm going to call that Newton meter A, Newton meter B, and Newton meter C. Okay, so to calculate the resultant of any two, so let's say I wanted to calculate the result, what is the resultant of, let's say, C and B. So the resultant of any two vectors in this setup is equal in magnitude to the reading on A. So if I'm pulling these two like this, and I'm pulling this one like this, when it's all kind of in equilibrium, the magnitude of the resultant of these two forces, so this, we're trying to pull it like this. So overall, we're trying to pull it roughly in this direction. So to get the magnitude of the combined of these two forces, or these two vectors, it's this fella, the magnitude that's on this Newton meter. And in terms of direction, it's opposite to the reading of this Newton meter. So this Newton meter is telling you that's the force of, let's say, 10 newtons pulling in this direction. And that means that these two forces here have a resultant force of 10 newtons pulling it in the opposite direction to this, because that's why things are keeping it in equilibrium. The resultant of these two forces is balanced by this fella here. Okay, an object, sneaky question again, an object is released with an initial velocity of 150 meters per second at an angle of 20 degrees to the horizontal. Resolve the velocity into horizontal and vertical components. Okay, so let's think of it as the hypotenuse of a right angle triangle, 150. And we're looking for what's the vertical, what's the horizontal. So we're going to need sine and tan. Silly old Harry. Chased. Sine and cosine. We don't need tan. Adjacent over opposite, because that's no good. That's 2 missing things. So let's go with the sine first. Sine is equal to opposite over hypotenuse. We know the hypotenuse. V here is, vertical component is the opposite, which is the thing we're looking for. So if I multiply h times the sine of the angle, which in this case is 20, this will give us the vertical component. So the hypotenuse is 150 times the sine of the angle 20 will give me the vertical component. So it has a vertical component of 51.30, can round it off there, and it's meters per second because it's velocity. And the horizontal component is going to be cosine. So the cosine of an angle theta is adjacent over hypotenuse. So this is what we're looking for, the horizontal. Sorry, bit mislabeling here with the horizontal versus hypotenuse. So the horizontal, or the adjacent here, and let's bring the h across. So the hypotenuse multiplied by cosine of angle theta will give us the adjacent, the horizontal component. So that's 150 multiplied by cosine of 20. So that's 140 0.95 meters per second. Now let's just identify them. That's the vertical component, and that's the horizontal component. I'm running out of paper. That'll do. Okay, what do we got? Calculate the magnitude and direction of the velocity of the object after 8 seconds. A sneaky question. It looks easier than it is. So they launch the object like that. 8 seconds later, what's happening? Okay, well, in these kind of questions, you can presume that there's no air resistance. So whatever the horizontal component is, it's not going to be changed. So in this case, our velocity in the horizontal direction, we calculated a moment ago as being 140.95 meters per second, and that's going to be unchanged. But that's not the case for the vertical. So let's deal with the vertical. We have an initial velocity in the vertical direction of 51.30 meters per second. So it's going up by 51.30 meters per second. But gravity is working against us here. Gravity is pulling it down with an acceleration of minus 9.8 meters per second squared. And they're asking us, what's the story 8 seconds later? So, like I said, the horizontal component is unchanged. It's 140.95. But the vertical component, we're going to have to work out. So we're looking for the final velocity here, v. So, unfortunately, I'm writing on the back of this at this point. We need to see which one of these guys is going to be our winner. And I think it's the first of the linear motion equations, v equals u plus at. So, v equals u plus at. Remember, this is all for the vertical direction. So that's the initial velocity of 51.3 plus minus 9.8 multiplied by 8. So 51.3 minus 8 multiplied by 9.8. So I got a vertical velocity of minus 27.1 meters per second. Now this makes sense. What's happening here is gravity's slowing it down. It's now actually on the down part of its arc. So when you throw a projectile, it goes up, reaches the peak, and then comes down again. So now we're at this point here where it's coming down, and this is its vertical velocity. So let's think of what's happening here. It's still moving across at a velocity of 140.95 meters per second, and now it's moving down at a velocity of 27.1 meters per second. So these are the two vectors associated with its horizontal and vertical, and its resultant, the total vector, is going to be this guy here. So we're going to use Pythagoras' theorem to get the magnitude, and then we can use a little bit of trig to get the angle. Okay, let's get the magnitude first. The square of these sides is equal to the square of the resultant of what we're looking for. So 140.95 squared plus 27.1 squared is equal to, let's call it resultant, to be squared. Now, we already have minus 27.1 in, so let's square that. Let's add that to 140.95 to be squared. And don't forget to get the square root of your answer. For me, that's a resultant of 143.531. So that's the magnitude. Let's figure out the direction. Whoosh. Okay, so we need to get, what is this angle here? Well, let's think of what we know. We know the opposite and we know the adjacent. So the tan is equal to opposite over adjacent. So let's put in our opposite over adjacent. 27.1 divided by adjacent of 140.95 gives us a value of, now to be careful here, so the answer is going to be tiny, 0.19. That is not your answer in degrees. That's the tan of your answer in degrees. So the tan of the angle we're looking for is 0.1922, blah, 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 blah. To get the actual value, let's go for shift tan answer. That gives us a value of 10.88 degrees in the vertical going down. Okay, now I need to check the number because that isn't ringing true for me for some reason. I remember it being slightly differently, but I think the technique is sound, so I'll verify that. I'm going to stop the video for a second, actually verify that's right, and then we'll do the final question.